Electricity, it's everywhere, right? It's this silent, invisible force that basically powers our entire modern world. It's this incredible form of energy that we can control, and it runs everything from the phone in your hand to the lights in your city. But what is it, really? Let's get into it.
Think about it. You probably do it a dozen times a day and never give it a second thought. You flick a switch, and boom, a dark room is instantly filled with light. It kind of feels like magic, but nope, it's just pure physics. So let's pull back the curtain on that everyday magic and really understand what's going on under the hood. Okay, first things first. We need to talk about the thing that's actually moving through all those wires. We call it electric current, and honestly, the best way to wrap your head around it is to just think of it as a flow. And the concept is super intuitive. We all get what a water current is, right? It's just the amount of water flowing through a river. Well, electric current is pretty much the same idea. But instead of water molecules, we're talking about a flow of tiny electric charges, usually electrons, moving through something like a copper wire. It's literally like a river of charge. Now, if you want to get technical, electric current, which we represent with the letter I, is the rate of that flow. It's how much charge is flowing past a certain point every second. We measure it in a unit called amperes, or just amps for short. So the more amps you have, the bigger that river of charge is. So for this current to actually go anywhere and, do something useful, it needs a path. We call that path an electric circuit. Think of it like a racetrack for these charges. You need a power source, like a battery, to get them moving in the first place. You need a switch, which is like the starting gate that opens or closes the track. And of course, you need something for the current to power, like a light bulb. But here's the absolute key. The whole thing has to be a continuous closed loop. If there's a break anywhere in that racetrack, the flow stops cold and the light goes out. This brings us to a really important question. Okay, we've got this flow, this current, but what makes it move in the first place? What's the actual driving force behind it all?
Let's be real. These charges aren't just going to move on their own. It's like water in a perfectly flat garden hose. It's just going to sit there. The electrons in a wire need a reason to move from one end to the other, so what is that reason?
Let's go right back to our trusty water analogy. How do you get water to flow? Well, you create a pressure difference, right? You put one end higher than the other, or you use a pump. Electricity works the exact same way. Charges flow because of a difference in what we can call electric pressure. The scientific name for this is potential difference. And this potential difference, which you probably know better as voltage, is the push that a power source like a battery provides. It's the energy that gets those charges up and moving. And we measure it in volts. So, higher voltage just means a bigger push. Simple as that. All right, so we've got the flow, which is the current, and we've got the push, which is the voltage. But there's one more critical piece to this whole puzzle. See, not every path is created equal. Some materials make it really, really difficult for the current to flow. That obstacle is what we call resistance. And yes, we're going back to the pipe analogy because it's just perfect for this. Imagine trying to push water through a huge, wide-open fire hose. Pretty easy, right? Low resistance. Now imagine trying to push that same amount of water through a tiny little coffee straw. It's way, way harder. That little straw is resisting the flow. That is exactly what electrical resistance does in a circuit.
The thing is, every single component in a circuit, even the wire itself, has at least a little bit of resistance. It's always putting up a bit of a fight. We measure this opposition in a unit called ohms. A really high ohm value means that material is putting up a huge fight and not much current is going to get through.
So, we have our three big players: current, the flow, voltage, the push, and resistance, the squeeze. You're probably wondering how they all fit together. Well, way back in 1827, a physicist named George Simon Ohm had the big aha moment that connects them all in a beautiful, simple way. And there it is, V equals I times R. It looks so simple, doesn't it? But this one profoundly powerful equation, Ohm's law, is the absolute cornerstone of all electronics. It tells us that these three things are perfectly related. For any given push or voltage, if you increase the squeeze, the resistance, then the flow of current has to go down.
Let's just see this in action. To make it super clear, imagine you've got a circuit with a regular battery, so the voltage isn't changing. If you suddenly swap out a component for one that has double the resistance, what happens? Well, the math says the current gets cut in half. It's a really simple inverse relationship that just makes sense. More squeeze means less flow.
Now, this idea of resistance isn't just some abstract number we pull out of thin air.
It's directly determined by the actual physical properties of the material the current is trying to flow through. So, what actually makes something a good conductor versus a bad one?
It really just boils down to three main physical properties of the conductor itself: how long it is, how thick it is, and of course the actual material it's made from. Let's take a quick look at each one.
First up, length. This one's pretty easy to imagine. Think of it like running an obstacle course. A short course is easier than a long one, right? It's the same for electrons. The longer the wire, the more stuff the charges have to push through, meaning more opposition. So, a longer wire always has more resistance. Next is thickness, or what scientists call its cross-sectional area. A thick wire is like a massive 8-lane superhighway. It gives the charges tons of room to flow, so there's less congestion. That means less resistance. A thin wire is like a tiny 1-lane country road. Everything gets backed up. That's why the cables used for high-power applications are always so thick. And finally, maybe the most important factor of all, the material itself. Every material has its own natural, built-in property called resistivity, and the differences between materials are just staggering. Copper is a fantastic conductor. It has incredibly low resistivity. It's like a freshly paved highway. But then you look at glass, an insulator, and its resistivity is trillions of times higher. It's basically a solid brick wall for electrons. And in between, you have useful alloys like nichrome.
And this brings us to a really brilliant real-world example. Why are the glowing red coils inside your toaster made from an alloy like nichrome instead of, say, superconductive copper? Well, it's because that alloy has higher resistance. All that squeezing and friction generates a ton of heat. Plus, it doesn't just burn up when it gets super hot. So in this case, the resistance isn't a bug, it's a feature. It's the whole reason you can make toast in the morning.
So the next time you flip a light switch, just remember what's happening in that instant. A push of voltage is creating a flow of current, which is being squeezed by resistance, all governed by one simple, elegant law. These fundamentals don't just turn on a light bulb. They power our computers, our hospitals, our entire civilization. It kind of makes you wonder, doesn't it? Knowing these basic rules, what new magic are we going to build next?